In this capsule on electronegativity, let's take a look at the stability of compounds, could be or ions. I started with anions. You can also talk about cations. Now, just to recap, in the previous video, we talked about electronegativity as one of the periodic properties of elements and how that electronegativity gave rise to what we call a polar covalent bond. Just to review that briefly, take a bond like carbon fluorine or carbon nitrogen or carbon oxygen. This is fluorine is an example of a halogen. So you can draw carbon fluorine, you can draw carbon chlorine, but many times in organic chemistry textbooks you may see it as a CX bond. X denotes a halogen. That's a general thing. So X can be fluorine, chlorine, bromine, or iodine. Okay, so I'll erase that. Go back to fluorine just to be specific. So in this different types of bonds, carbon with fluorine, different elements, all these elements, fluorine, nitrogen, oxygen, chlorine, are more electronegative than carbon, as a result of which the two electrons, electrons can be considered as particles or clouds. So the electrons are polarized towards the other element. So yeah, they're sharing these two electrons form a bond, but then once the bond is formed, it's more polarized towards fluorine, for example. So fluorine will have a partial negative charge, carbon will have a partial positive charge, resulting in a polar covalent bond. So it is true with carbon nitrogen, carbon oxygen. So this is a result of electronegativity. One result of electronegativity, polarity of bonds, polar covalent bonds. Talk about more about polarity in other videos too, but this is like a review of what happened in the previous video. So let's move on from that point. So yeah, different elements have different electronegativities. How does that electronegativity of an element influence the stability of different anions? Anions are ions that have a negative charge on them. So I'll draw 4 anions to start with. Fluoride. I'll just do one thing. I'll come to that. So I'll draw the elements first. Carbon, nitrogen, oxygen, fluorine, in that order. So left to right. Fluorine is the most electronegative. So, fluorine forms only one bond. And I'll also draw the compounds with just hydrogens on them. The simple compounds that have, maybe I need more real estate. So I'll draw the simplest compounds with this, like CH4, carbon with 4 hydrogens, nitrogen with 3 hydrogens, oxygen with 2 hydrogens, fluorine with 1 hydrogen. So, this is one series of compounds. Now, what we are doing further is, I want to see the effect of electronegativity on the ions. Let's take these ions. So CH3 minus, NH2 minus, these are all anions, right? Which are being derived from these compounds, these neutral compounds. And I'm drawing the ions derived from these compounds shown in the above row. So hydroxide and fluoride. I just removed a H plus I removed a H plus, like H plus. For example, you can do this by removing H plus. How, we'll talk about that later, but some, let's say, a strong base is coming in, removing a proton from CH4, you get CH3 minus, like Now, the point of this video is how does electronegativity help us in predicting the stability of these anions, these four anions. Now, notice, what do you notice? In each ion, the negative charge is on the element, in this one carbon, nitrogen, oxygen, fluorine. What do we know about electronegativity? Electronegativity increases this way. So, fluorine has the highest electronegativity and it is better able to tolerate that, it can accommodate that negative charge better than oxygen. Oxygen in turn can accommodate the negative charge better than nitrogen, and nitrogen better than carbon. So we come to a fundamental concept in organic chemistry, stability. We come across this one so often, and we come up with different ways of explaining stability. Electronegativity is not the only thing that can explain stability. There are various ways of explaining stability, and we invoke different explanations for different types of compounds. In different situations, different explanations. So, do not be married to electronegativity. We invoke different concepts to explain the stability of different types of compounds. Okay, so we are invoking electronegativity to explain this ions. Which one is most stable? Fluoride is most stable because fluorine has the highest electronegativity, followed by fluorine. Fluoride is more stable than hydroxide. Hydroxide is more stable than amide, NH2 minus, which is more stable than the ions. So we're talking about stability often. Okay. So we need to keep various explanations for stability in our mind and take out whatever is appropriate to explain a situation. So in this case, electronegativity. Okay. Now I'll draw a different set of compounds to refine this further. In this example, the negative charge is on the element fluorine, on oxygen, on nitrogen, on carbon. Okay. Now, in the next example, we will do something slightly different. We will draw four structures of ions, four different ions. Okay, what do I have here? I have CH3O minus. Okay, and then I want to complicate things a bit. Fluorine, CH2O minus, chlorine, CH2O minus, bromine. Okay. Now I have four ions here, four ions. In all the four ions, the negative charge is on oxygen. So if we just focus on the oxygen only, and if we think about, hey, the negative charge is an oxygen atom, so how do we explain which one is more stable than other? How do we order these four ions in stability order? How do we do that? In the previous example, the ions are on different elements, like this. So here it was easy. Fluorine is most electronegative, so that's more stable, and since we have the order, we were able to explain this one easily. But in this case, something has changed. The ion, the negative charge, is on the same atom, oxygen. Then how do we do this? Now, we try to find what is different Here you have CH3O minus, plain carbon. Here you have the carbon connected to fluorine. In the next one, carbon is connected to chlorine, carbon is connected to bromine. So we want to see, fluorine is the most electronegative element, so it can pull, now we think about electron as a cloud. So whatever the electron density on the oxygen, okay, is being pulled by the fluorine towards itself. Okay, so if it's a cloud, it doesn't need to, it can move across the molecule. So fluorine can pull that electron cloud away from the oxygen. Here, chlorine can pull the electron cloud away from the oxygen. Bromine can also do that. Carbon is in this example, carbon is our base case. Okay, we have different elements with different electronegativities that can pull the negative charge away from oxygen and towards them. So what is happening? These elements, fluorine, chlorine, bromine, they are removing the electron cloud from oxygen towards themselves. So the electron cloud is no longer stationary, it's sort of spread out. It's no longer fixed on the oxygen atom in these three cases. In the first one, yeah, more or less. In the other three examples, these halogens are pulling the electron cloud away. So the negative charge is spread out, which makes it more stable. So when a negative charge is spread out, okay, and let me introduce another word here. Okay, the term or terms is localized versus delocalized. Okay, this is the terms used. So in the first example, CH3O minus, the negative charge here is localized on the oxygen. In the other three examples, fluorine, chlorine, bromine, are removing the electron density from the oxygen. So we say the electron cloud is somewhat delocalized, and that is due to the electronegativity of these elements. So now, which one will be more effective of these three? Which one will be most effective in delocalizing or removing the electron density from oxygen? Fluorine. So this compound, let's call this compound A, or ion. This ion is most stable. Okay. Now, if the charge is localized, let me add one more thing. If the charge is localized, then it's not stable, it's in a hurry to react. There's a negative charge, it's in a hurry to react with something positive. But if it is delocalized, that is removed, that adjunct is removed, which means it's more stable. Okay? So fluorine is the most stable because it has the highest electronegativity, followed by chlorine. So ion A is more stable than ion B, which is more stable than ion C, and which is more stable than the first one, which we call it D. So A, B, C, D. So if the questions come like this, okay, so we invoke something fundamental to answer a given question. In this case, in the two examples that we have seen here, that fundamental concept is electronegativity, and how we use it to explain the stability of these ions. Okay. Ion A is most stable because fluorine is the most electronegative element. It's most effective in removing the electron density from A. And there's a name for these things. This type of thing is, as we talk about this, we also talk about nomenclature, like what we saw, localized and delocalized. And here the effect, whatever this effect, fluorine is removing electrons away, chlorine is doing that, bromine is doing that. So there's a word for that, inductive effect. Okay. And we qualify it with a negative. So there is also a positive inductive effect, a negative inductive effect. This is what is negative inductive effect. The ability of these halogens to remove electrons from a given place, from a given atom. It's called negative inductive effect. You can think about this as induce. The electrons that are on these oxygen atoms are being induced away from wherever they are on the oxygen atom. So a negative inductive effect. So electronegativity gave rise to polar covalent bonds. Electronegativity explains the stability of ions, which ions are more stable than others, and they exert that influence via inductive effect. One way. Okay. So we stop here. In the next video, we'll see different examples, probably 2 more examples, and then we can stop electronegativity discussion. See you in the next video.